Okay, so this is part 2 of the partial pressures and ideal gas podcast. Here is another um, particle velocity distribution, and as you could tell, the higher the temperature, because it's various temperatures. We would expect the curve with the higher temperature to have a higher speed. So this curve right here would represent the gas that is warmest, and then the gas that's coldest would be the one all the way on the left, because it's going to have a smaller speed. Just because you have a higher temperature or smaller temperature doesn't affect the amount of moles, because the area looks the same. We also talked about what this line represents. If you draw a dashed line from the peak all the way to the bottom, this represents the average, and it represents that most of the cold gas particles have this speed down here. Okay, so it says that most number of gas particles is high, so that most of the gas particles would have this speed. Most of these gas particles at intermediate temperature would have this speed. Most warm gas particles would have this speed. So that's what this dashed line represents, and that's how you interpret the data in this particular graph. So the next thing we learned is how to do stoichiometry and how to use the ideal gas equation. And the first thing I've taught you guys is always write what's given to you and what you want. It says what volume of hydrogen. So we want the volume, but we also want hydrogen's volume. And what volume of hydrogen will react with carbon at this many torrs, this temperature, and you want to yield 42 grams of pentane. First of all, you have pentane, and you have hydrogen, so you know you're going to be using a mole ratio somewhere. So because you have pressure, temperature, and moles, essentially this is moles because you convert grams into moles, then you could use PV equals nRT, and you could solve for V, which is V equals nRT. So let's look at this piece by piece. So let's look at the N first if you want. So N is 42 grams of pentane, which is this one. So if this is hydrogen, this is carbon, then this has to be pentane. So let's put, I'm just going to put NP for pentane. And I don't want moles of pentane, I want moles of hydrogen, because I want the volume in hydrogen. So when you find a molar mass of this, 12 times 5 is 60, plus 12 is 72. 1 mole of pentane, and that gives us moles of pentane. But we don't want moles of pentane, we want moles of hydrogen. So you do one extra step. 1 mole of pentane, because there's a 1 here, has 6 moles of H2. And when you do the math, you get 3.5 mole of H2. Okay? Okay. So we have N. R is gonna depend on the pressure. There is no R value that has torr in it, so I'm gonna convert that into atmospheres. So I could use one of the R values that are in my notes. This one, R is equal to 0.0821 atmospheres, mole, Kelvin, something like that. And then I need to convert into atmosphere. So 981 torr, 760 torr is found in 1 atmosphere. So when we do the math, you get 1.29 atmospheres. So far we have moles, we have atmospheres. Do we have liters? No, because that's what we want. And then Kelvin, which is just Celsius added by 273, which is 607. So that's our T. So now we could plug everything into this equation. V is equal to N, which is 3.5 moles, times R, which is 0.0821, times T, which is 607, and divided by P, which is 1.29 atmosphere. Okay, so when you do the math, you get a number, and so 3.5 times 0.0821 times 607, and then you hit equals, and then you divide by what's at the bottom, one at a time, and I got 135 liters. Okay. Alright, so next problem. See what the next problem is. So the next problem that we did is we started to include one new concept that we learned, and this new concept is called Dalton's law of partial pressures. So what it's saying is that if you have gas 1 and gas 2, those are partial pressures. For example, PO2 and PN2, oxygen and nitrogen. When you add them together, you get the pressure of the whole mixture. The same thing with the moles. If you have moles of oxygen and moles of nitrogen, you could just add them together. What we learned in class is something called the mole fraction. And the mole fraction, what it's saying is that the mole fraction, which is x, it could be a fraction, or in this case, it has to be a decimal. So it could be 0.7. And 0.7 represents 70%. So 70% of a gas. So that's what this is representing. And gas, so how many gas particles of oxygen is there with respect to the total? So let's say it's 70 moles out of 100 moles of gas, then it's going to be 70% oxygen, let's say. And that's going to be 0.7 oxygen. That's going to be the mole fraction, 0.7. That represents the quantity of a specific gas in a whole mixture. So what we did is I did this example, and it says that the mole fraction of nitrogen is 78%, which in this case is that. If the total pressure is 760, what is the partial pressure of N2? So if we look back at the previous slide, where X of nitrogen is equal to N of nitrogen over N total. So what happens is that when you have nitrogen's moles divided by the entire moles, you get 78%. So we don't have to use this. We could just plug in for this. So what you do is you put the total, P total, times the mole fraction, is going to give us the pressure of just that substance. So P total is going to be 760 torr, and the mole fraction is going to be 0.78. And so when you multiply them, you get the mole fraction, which in this case is 592 torr. So this is the mole fraction for nitrogen. Okay, so this represents nitrogen. Okay, so that might have been a little bit confusing. So that's why we have more problems. And here's another example. So for this one, it says data from a gas matrix found below, where you have 1.5 mole percent. So you have 1.5% for CO2, 18% for O2, and 80.5% for argon. So when you add all of these up, you get 100% essentially, right? So what you could do is you do 1.5 divided by 100, 18 divided by 100, 80.5 divided by 100, and that gives you your mole fraction. So the mole fraction for this one will be 0.0 0.015. 1, 2, 3. No, missing a 0 here. And for this one, it's going to be 0.018. And this one's going to be 0.805. So these are the mole fractions. This is the mole fraction for CO2. This is the mole fraction for O2. This is the mole fraction for argon. And if you multiply these by the total pressure, you'll get the partial pressure. So it says find the partial pressure of O2 if the mixture has a total pressure of this. So you're going to take the total multiplied by the mole fraction of oxygen, which is this one. And that's going to give you the partial pressure of just oxygen in that mixture. So when we do this, 7.5 times 0.018, you get 13.4 torr. Let me actually double check this. 1, 2, 3, 18%. 0.018 times. Yeah, so that'll be the partial pressure. And if you want to find the partial pressure of everything else, you just multiply this total by that, this total by that, and you'll get the partial pressures of everything else. In part B, it says if the atmosphere is held in a 121 liter space at 295 Kelvin, how many moles of O2 is that? So we already found the partial pressure of O2, so that's good. So again, if I didn't give you this question up here, you would still have to figure this out to answer this question. So we have the volume, we have the temperature. All we have to do is use PV equals nRT. And it wants it, so we want moles, we want N, so you divide by RT. And then I'm just going to rewrite it here. So pressure is 13.4 torr. But again, we don't want torr, we want atmosphere. So I'm converting this into atmospheres. So that's the pressure. I'm just going to put it all under the same formula. And then V is 121 liters. And I'm dividing all of this by R, which is 0.0821, and T, which is 295. It's already in Kelvin, so I don't have to do anything to it. And then when you solve all of that, so 13.4 divided by 760 multiplied by 121 divided by 0.0821 divided by 295, you get 0.088 moles. Okay, so that's going to be your answer. And that's where we left off.